So today I'm going to talk about a multi-epoch study of radio-quiet AGN, a small sample of radio-quiet AGN. And let me just introduce a little the kind of sources I'm going to talk about today. So you must be all very familiar with this particular slide. But basically, it was in the 1940s that astronomers like Carl Seyferts and others realized that not all galaxies have this are like this, where there is an increased stellar density towards the center, but rather a fraction of them seem to have a very overwhelmingly bright nucleus. As you can see here, this point source here, which is showing up like a star. And in fact, when these galaxies were basically taken shallow exposures of, only the star-like nucleus was visible. And so these sources came to be known as quasi-stellar objects, or QSOs. Another peculiarity of these galaxies was that where normal galaxies, the spectra show a lot of absorption lines, as you can see here. The spectra is dominated by absorption lines, and these come from the stellar photospheres that make that galaxy. The spectra of these active galaxies, on the other hand, are dominated by emission lines, as you can see here. And these emission lines are both narrow, which means velocity widths of a few hundred kilometers per second, as well as broad, as you can see here, with broad bases, which can be several thousands of kilometers per second. So since it was Carl Seifert who realized this kind of peculiar sort of spiral galaxy with these properties, these spiral galaxies with active nuclei are now called Seifert galaxies. So these Seifert galaxies are going to be a prime focus of the talk today. And it was at least 20 years later, this field really took off when radio telescopes came about, and radio imaging was sensitive enough to actually see faint radio emission from these galaxies. It was soon found that these active galaxies emitted radio waves. So as you can see here on the left, this is actually an image of an elliptical galaxy in the blue. And the red emission that you see is radio emission, which is being ejected from the active nucleus in this galaxy. But this was actually only 15% of the active galaxies which showed structures like this. Most of the active galaxies were on the other hand, like the source on the right. So you can see very clearly the optical host galaxy. You see the spiral arms of the host galaxy. And the red emission here is hot X-ray emitting gas. And the pink-blue emission is radio emission. So here you also see bipolar radio outflows. But they're much smaller in extent compared to these sources which are found in elliptical galaxies. And this is the vast majority of active galaxies. And these are classified as radio-quiet AGN. Even though they're not really radio-quiet, they do emit radio emission, but the extent of the radio outflows is much smaller compared to the host galaxies themselves. So this is a very kind of persistent open problem in AGN, active galactic nuclear research, is why are most AGN of this sort radio-quiet AGN, whereas only a small fraction of sources are of this sort, which are known as radio-loud AGN, where the jets can be, hundreds of kiloparsecs in extent and basically traversing intergalactic extents. Sorry. Basically, the distance between galaxies are covered by these radio jets. So the question of the radio-loud, radio-quiet divide is a very important one in AGN physics. But I'm going to focus on the radio-quiet AGN for this talk, and I'll show how that also kind of gives insights on why the majority of AGN are of this sort. So before I get there, let me tell you a little bit about the optical spectra of these radioquiet AGN. So in my talk today, I'm referring, when I say radioquiet AGN, I refer to the Seyfert galaxies and LINERs. LINERs stands for low ionization nuclear emission line regions, which I will just tell you a little bit about. The Seyfert galaxies, this spectra I already showed you in the previous slides, comes primarily in these two broad categories. So there is one type of Seyfert galaxy which shows narrow emission lines along with broad emission lines, like you see here. Whereas there's another type of Seyfert galaxy which shows only narrow lines and not broad lines. So the top one is referred to as a type 1 Seyfert galaxy, and the bottom one is referred to as a type 2 Seyfert galaxy. And on the right panels, you can see what a liner looks like. So on the top is a Seyfert 2 type of galaxy, which is basically dominated by narrow emission lines. The liner nucleus, or rather the liner spectrum, is dominated by low ionization lines. So as you can see here, if you compare the O2 and the O2 in the liner, the O2 is much more prominent, for example, compared to the O3. Similarly for the N2 and S2 lines. So this, I just wanted to flash this to kind of give you a sense of the regions we're talking about, which I will be, discussing more in the subsequent slides. So this is a cartoon to show what we believe is the active nucleus with a supermassive black hole, which is accreting gas. And there are the emission lines that we see actually are coming from gas clouds moving around these black holes. And the fast moving clouds are what give rise to the broad lines that you see in the spectrum. And this region is called the broadline region, or BLR. And the narrow lines that you see in the spectra are coming from the narrow line region, or the NLR. In addition, we believe that there is some kind of obscuration which hides the BLR from our lines of sight for certain sources. And those are the sources which then produce Seyfert type 2 spectrum. And when these sources are oriented in such a way that the torus is not obscuring the broadline region, then you see a Seyfert type 1 spectrum with broad and narrow lines. So, so this is also known as the unification model for AGN. So today, the sources I'm going to talk about is a small sample of Seyferts and liners, and all of them happen to be type 2. So they just have narrow lines. The sample is called KISSR sample, or KPNO Internal Spectroscopic Survey, the red, and so basically we obtained a sample of 9 sources from this larger sample. We identified these from the SDSS spectra as having double peak lines. So as you can see on the right side, this is the spectrum of one of those sources. And apart from, I mean, you see the narrow lines, but the narrow lines have split peaks, as you can see here. So this is work that was initiated by our colleagues at IIA, Maushmi Das, and she actually went through the SDSS spectra of the large sample of sources and identified by eye this sample of double peaked Seyferts. So it was a small sample to begin with, but they were very interesting because when you see double peak lines in the spectrum, these could be candidates for having binary black holes. And so basically you have, instead of the model that I showed you in the previous slides of an AGN with narrow line regions, so you would have 2 black holes with narrow line regions, and those would be the reason why you see a split in the narrow lines. Also, there could be other explanations for having these double peaks. For example, the narrow line region itself, which I showed you in the cartoon earlier, may not be in that particular morphology and maybe a little more flattened, like disc-like, and so maybe that will give rise to these double peaks. Or there could be another reason for the splitting of these line peaks, and that could be that the jet is somehow pushing the narrow line gas clouds in two opposite directions and then causing split in the lines. It was because these are interesting candidates for binary black holes that we kind of decided to carry out high resolution radio observations of this sample. And so we got two frequency, we proposed for two frequency data using the very long baseline array, which is the VLBI array. And just recently, in fact, the last observation was last month. We have now obtained two epochs of these sample galaxies. So the first epoch observations have been published in several papers over the years, and I'll just talk a little bit about what we have found in these works. So before I get to the images themselves, let me just tell you a little bit about VLBI, very long baseline interferometry. And VLBI is where you carry out interferometric observations using radio telescopes which are actually not connected to each other, for example, by optical fibers. So this is, for example, it's not like the GMRT, which is a connected interferometer, but rather the telescopes are widely separated by thousands of kilometers. And the data are recorded on magnetic tapes at these individual telescopes. The only condition for this to work is that the data has to be time-stamped very, very with a very high accuracy. So you need hydrogen laser clocks. And then you can later play the tapes back with these accurate timestamps and then correlate the data. So the only constraint here is, of course, in this case, the diameter of the Earth, but even that is not a constraint because we have also carried out space VLBI observations. The only constraint is that you have to have these telescopes intersect the same wavefront from your AGN. So because of these very large baselines, you can get very high resolutions of the order of milliarc seconds and even hundreds of microarc seconds, which translates to, for these sources, to parsec scales and subparsec scales. So the telescope that we used for carrying out VLBI is VLBA, Very Long Baseline Array, which are basically 10 telescopes which are in the US, as shown on the top. So looking at the sample sources themselves, these are SDSS images of the Seyfert galaxies in that small sample. And so you can see very nicely the spiral arms in several of them, dust lanes, etc. But you can see that these are spiral galaxies and dust galaxies. These are the liners in the sample, and at least two of them, you can see that they actually have, they are in some kind of merging galaxies and have multiple nuclei. So this slide is now showing you the same optical images superimposed by radio contours. And these radio contours are from Very Large Array first survey at 1.4 gigahertz. So basically, the VLA does not resolve any of this emission. It shows a point source at the center of the galaxy. So there is some radio emission coming from the AGN and these galaxies. This particular galaxy, it's KISSR 872. I'll be talking a little more about this, but basically it shows optical nuclei. You can see two optical nuclei, but the radio emission, so this is the same galaxy, radio emission is only coming from one of those nuclei. So that is the one we've looked at with VLBI. Okay, so of all these, and I think one more thing I do need to mention, which I will also come to in the later slides, is that all these sources are extremely radio weak. So these are just millijansky sources, and just a few millijanskys, in fact, in total flux densities. So very, very weak radio sources. So truly radio quiet AGN. Now, of all these sources which are candidates for binary black holes, we found only one of them could actually maybe be a candidate for a binary black hole. But still, this definitely needs still more work and more additional observations to confirm. But basically, what we found in this source galaxy KISSR 102 is that this is a liner galaxy. It also already showed the presence of two optical nuclei. So this is called as N1 and N2. And just like the previous galaxy I mentioned, only one of these nuclei actually emits radio waves. And this is the nucleus we focused on. So the N1, the separation between N1 and N2 is around 1.5 kiloparsecs. And this particular source is also has also been classified as an offset AGN, which means that the AGN emission lines are offset from the galactic absorption lines by a few hundred kilometers per second. So this is already an interesting source. We found radio emission only from one of these nuclei, N1. And a VLBI image, I'm not sure if this is showing very clearly, but basically this central panel, or rather, this panel shows this slightly better. We see a barely resolved two-component structure in VLBI, and we call them A and B at 1.5 gigahertz. In the 5 gigahertz image, we found that only one of these two nuclei, actually just this component A, seems to be emitting, and this itself also is kind of barely resolved structure, a barely resolved structure. So, so you can see there are many things here. So two optical nuclei, 1.5 kiloparsec apart. The one of the nuclei, N1, VLBI shows two components A and B. The separation of these two components is around 5 parsec. Okay, and the component A itself at higher resolution at 5 gigahertz then also shows some kind of bare resolved structure with the separation of 1.5 parsec. So this source, I'll now tell you a little bit about the latest data that we have on this source, which is it's basically 4 years later. And so these are the new images at 1.5 gigahertz and 5 gigahertz. So interestingly, KISSR in the second epoch image of KISSR 102 does not really show any change in those two components A and B that we found. The separation is around 4.5 parsec. So given the errors, there is no change in the separation of these components, which is interesting because if A and B were actually a core jet structure, we would have expected some motion, but there seems to be none over the 4-year time scale. At the 5 gigahertz image, what we saw earlier of like another barely resolved two components, we don't see that clearly. It seems to suggest a single component. So it's not clear if there are two A1 and A2 components anymore in the new data. So, what we had found earlier also was that when we took the spectra of KISSR 102 using 1.5 and 5 gigahertz, we found that there seemed to be this component, which was also which was what resolved into A1, A2. The component A seemed to have an inverted spectrum of 0.61. And then since this second component was not detected at 5 gigahertz, we could only get a spectral index limit, which was pretty steep, of around steeper than -1.6. So in fact, that also is another piece of evidence which suggests that this is not just a core jet structure, because the spectral index difference between these two components is very steep. It's a very sharp change in the spectral index. The second epoch observations also kind of are consistent with that result. The spectrum of this component continues to stay inverted, and there is no detection of the second component. So both the total intensity and the spectral index so far are consistent with the possibility of a dual black hole in this source. But what was very interesting was for the rest of the sources, we haven't found any indications of double radio cores. In fact, what we found was a prevalence of jets. So this is already very interesting because, like I mentioned in this top thing, these are very, very faint radio sources. So the total flux density on kiloparsec scales is only 4 millijanskis. This is actually one of the brighter ones. So the fainter ones go around 2 millijanskis. But when you look at them with VLBI, they seem to show one-sided jets. Okay, so to give you some idea, this usually VLBI will detect only the highest surface brightness emission. So this just means that it doesn't mean that there is no emission here. It's just that it's not being picked up with VLBI. So you pick up only the brightest portions of it, and you can see very clearly that there is some kind of a curved jet. The extent of this jet is also very large. In this particular source, KISSR 434, this is of the order of 150 parsec. So it's a large curved jet. And also it's almost always we have found the sources to not have any counter jet emission. So you don't have emission on the other side, only on one side. And the second interesting thing was that when you look at the second frequency data and obtain spectral indices, the spectral index is very steep. This is also peculiar because normally when you look at AGN, the core emission is inverted or flat, and the jet emission is usually steep. But in all our VLBI data, we found that even the core regions are steep spectrum. Then the next question is, could this one-sidedness be explained by relativistic jet motion? Which is how normally VLBI observations of radio loud AGN are inferred. So in radio loud AGN, one-sidedness is very common, and that's ascribed to Doppler boosting effects, which is boosting emission from the jet which is approaching us, and actually Doppler dimming the emission from the counter jet. So could this also be true for radio quiet AGN is the question. We don't know yet, but if it's true, that's very interesting. And so we inferred some, of course, there is no counter-jet emission, so we can't really obtain a jet to counter-jet brightness ratio, but we can get limits. And so we tried getting limits for this. And once you have that, and if you assume some kind of jet inclination, you can get an estimate of the speed of the jet, which would give rise to this one-sidedness. So the angle that we've assumed is around 50 degrees. And this comes from the expected torus half opening angle. Since these are Seyfert type 2s, that means they don't show broad lines. We can assume that the inclinations have to be greater than 50 degrees, as the torus half opening angles are supposed to be around 50 degrees. So for this kind of theta, this jet speeds that are derived are pretty large. So in this particular source, it's greater than 0.75 c speed of light. So that's already very different and unexpected, because in these radio quiet AGN, you don't expect them to have very fast jets. This is another source, KISSR 872, where again we found some very, similar and interesting results. Again, only 5 millijanskis in the first VLA first, so kiloparsec scales only 5 millijanskis. But VLBI shows a 200 parsec long jet, and the spectral index image shows that the spectrum is steep throughout, of the order of -0.7. So overall, what we found was that in the we detected, out of the 9, we detected 8 of them with VLBI, and there was, in more than 60% of them, there seems to be some presence of a jet, and it's typically one-sided, as shown here in KISSR 618. This is one of the weaker sources of with having only 2.5 millijanskis on kiloparsec scales. So for this whole sample, we found that assuming inclinations of around 50 degrees, jet speeds could range from 0.003 C to 0.7 C, assuming that the one-sidedness is due to Doppler boosting / dimming effects. We don't know if that's real, if that's true, but these are interesting limits. So since these sources also had optical spectroscopic data from SDSS, we could carry out an emission line analysis. And here, Smita Subramaniam from IIA, she was very, very helpful with this. So basically, these are images showing some results from the mapping software, which is a plasma modeling code. And what's plotted here are basically line ratios for a given source and a particular model. And in this case, we found most of the sources which show jets are also well fit by what is known as the shock plus precursor model. So it looks like it's not direct shocks from the jets, but shock plus precursor, where the post-shock gas actually then photoionizes the medium ahead of it. So this kind of shock plus precursor model seems to fit the emission line ratios for nearly all the sources which show VLBI jets. So this was a very interesting result. And moreover, we found from the optical spectra that the line separations, the peak separations, were of the order of a few hundred kilometers per second, which are typically much smaller than what the jet speeds are expected to be. Even if you didn't take the speeds that we have derived from our study, but took other estimates from the literature, even then these the line speed separations are much smaller compared to the jet speeds in even in radio quiet AGN. So it looks like that either this emission line gas, the narrow line gas clouds, are being definitely pushed by the jet, but not always ahead of the jet, but maybe laterally. Or it could be that the emission line gas itself could be arising in some kind of a wider outflow, or there could be a wind which is coming from the accretion disk and then pushing the narrow line gas clouds away. So it's not clear exactly what's happening, but looks like there could be what are known as nested biconical outflows. This is a suggestion which has been in the literature for double-peaked emission line AGN in general. And this could actually explain our results as well. So it could be that there is prevalence of both jets and winds in these radio quiet AGN. So now I'm going to flash a couple of interesting results which from the second epoch data that we've got. So for example, in KISSR 618, I had shown you this image earlier. The new data also shows some kind of a core jet structure, but it seems like some change has happened in the so-called jet direction. So that's very interesting. This is 4 years later. Such changes in jet direction are very common in the radio loud AGN, for example. Blazars, when they're observed with multi-epoch VLBI, do show changes in jet direction on small time scales of a few years. That seems to be happening. But another thing that seems to be very interesting in these new data are that especially in the core region, there is the jet itself doesn't appear always to be collimated. It seems to always, or not always, in several instances, have also some kind of a broader component at the base. As you can see here, there is some, extension in a different direction from the jet. So that is very interesting. Sorry. Yeah.
You have 2 minutes.
Yes. I'll be done very quickly now. And so another source here, which we had looked at in the Epoch I, KISSR 1494, showed just a very weak point source in our first epoch observations. And we had suggested, because it was deep spectrum emission, single knot, we had suggested that this could be actually the base of a wind in our 2015 paper. Interestingly, the new data finds some kind of a jet along with this broad base. So that's actually overall very consistent with whatever we are already inferring from the emission line data. So this is the new image several years later. The KISSR 872, which I showed you, which had this long jet, this is the new image several years later, as you can see. Again here, you see some of the jet components, so not all of the jet's components seem to be present in the new data. There are some differences in sensitivity of the new data also, but even then, but most interestingly, the spectrum continues to stay steep. But maybe there is a little bit of spectral flattening in this particular source. It was minus 0.7 or something earlier, and now it's minus 0.3. Another thing we notice again here is also, as you can see here from the contours itself, there is you do see more than one component at the base of the jet. I mean, could this be a wind? We don't know. So finally, I come to this last source, which I wanted to mention, which turns out to be super interesting. Sorry, KISSR 872. This is the previous observation from 31st December 2018, and we saw this core jet structure. So J0, the separation of these components was around 13 parsec. In our new data from November, the separation seems to have increased to 15 parsec, which implies a jet expansion speed of 1.7 C. So this was very, very unexpected. In fact, if you look at this component very close to the core, which was not very clearly resolved at all in the first epoch, now it's a little better resolved. If you do believe that this is the same component which was seen earlier, the expansion speed is actually 3.5 C. So anyway, this I would like to confirm this, but the expansion speed of J naught is 1.7 C. This makes this particular galaxy, which is a liner, I think the first ever to show superluminal motion. There's only one more Seyfert galaxy which has been suggested to show superluminal motion. That's Zwicky 2, which is actually not really a radio quiet AGN. It's a little bit of an intermediate object. And so this makes our results extremely unexpected and very exciting. So we were kind of inferring that these jets could be relativistic, and at least in one source, we see some signatures of this possibly being true. So let me summarize. Of the 8 detected double-peaked AGN, only one of them, so around 10% of this small sample, shows possible signatures of having or hosting a binary black hole. But 75% of these sources show signatures of one-sided jets, parsec scale jets. Could this jet-sidedness be an indication of Doppler boosting effects? It looks like, at least in a couple sources, that there could be a superluminal jet motion in these galaxies. So that would actually be consistent with this idea. The plasma modeling codes are suggesting that the shock plus precursor models can explain the emission-line ratios in these sources, which means that there is some kind of a jet plus wind medium interaction taking place in these radio quiet AGN, which could actually be the reason for the line splits. So overall, we conclude, first of all, that radio quiet AGN are super interesting, and they're actually energetically capable of influencing their the medium around them. Even though they are radio weak, they do influence the medium around them, and so that makes them agents for radio AGN feedback, which has not been really taken so seriously at all for radio quiet AGN so far in the literature. So with that, I will stop, and I'm happy to take questions.
Thanks. Yeah.
Hi, Preeti. This is Surajit here.
Hi.
Yeah. Hi. Actually, I saw this in view of your images. You draw the jet direction. So, where there are many components available, it is fine. You are following that line as a jet emission. But when there is nothing available, I mean, only few contours in the central source is available. How we are following? Is it the direction of the knots in several contours, or
Okay, so if I understand your question, it's you were wondering if those jets are actually, I mean, how robust those identifications are, right?
Yeah.
Right. No, so it's very, very true that it's some of the sources seem to show just very mild extensions, and but so we've kind of tentatively called them as jets. But this is also very typical of VLBI observations of these sources, actually. So since you're going to pick up only the brightest jet knot emission, sometimes you may not, the jet identification is not trivial, and especially in these radioactive agents, which are very radio weak. So that is an issue for sure. If you want to know how we robustly did this, I mean, we've definitely not followed. For example, a jet is considered a jet in kiloparsec scale observations as some feature which is like 4 times longer than its wider, right? So we've not always kind of stuck to that. It's more like a faint extension in the radio emission. So that's what we call the jet. But so far, even the second epoch observations seem to be consistent. Sometimes what we didn't see the first time, we're seeing in the second one. But yeah, overall, I agree that jet identification is not trivial.
There is a question in the mailbox there. Yeah.
Did you say I could ask a question? I couldn't hear.
Go ahead. Yeah.
Okay, so I had 2 questions, Preeti. One is the 2 epoch data that you showed. Are the image RMSs comparable in the 2 epochs for those images? Like image-wise, are they comparable?
Yeah.
And the second question is, there was one source where you talked about some spectral index anomalies. I was wondering if they could be explained by one of the components being supernova instead of related to the AGN itself.
Okay, yeah. Thanks. So the sensitivity of these 2 epochs are not always the same, because we did, in some sources, we have, been able to get all the 10 antennas, and some of them have only, 7 or 8 VLBI antennas. So the sensitivity is not the same. So some of the new images actually are less sensitive than the previous data. But interestingly, we have found we are able to find, the jets are bright enough for us to kind of even see them in the second epoch, which was interesting. But the sensitivity, there is a difference. We can identify individual, like the ones where I mentioned superluminal motion. That particular source is definitely comparable, but there are some others which are not. That's the first. Second, about the supernova. So most of these, the sources where I mean, almost all of them are not just points. I mean, the ones which we have spectra for are also the ones which are not just point sources. I mean, they have some kind of extension. So we think those are core jet structures. And then those core jet structures are the ones we found to be steep spectrum. The other point sources, most of the point sources, or rather the unresolved sources, we found also were not detected at the second frequencies. So there we could only get, limits on the alpha, and that was steep. But I don't see most of these VLBI data, when you detect some kind of even point sources, it's with the high brightness temperatures that are involved, I think it's very unlikely that these are supernovae. So that's the other thing. I mean, but there are many small things I could discuss maybe with you individually later. But
okay, maybe one more question.
I was just remembering NGC 613, if you remember, which showed some emission of starburst origin. Yeah, thanks.
Okay, yeah.
Okay, we have one final question. Asrikma?
Preeti, I was intrigued by your last conclusion. That is in terms of radio quiet AGN feedback. Your sample shows emergence of jet-like features in two epochs, but if we were to look at the historical record on radio quiet AGNs, is there a way to talk about the time scale emergence of such jet features? In other words, the duty cycle of activity in radio quiet systems, and can that be used in the longer calculations of radio quiet AGN feedback? Thank you.
Yes, yes. No, so that's perfect. That's a great question. And we have found that most of these, low luminosity agents seem to also show a lot of what is known as episodic activity. So they seem to, emit jets. Jets are ejected, and also multiple times. And not all the times are the jet directions the same. So there are changes in jet direction as well. So I think, so that's an excellent question. I think based on not just this result, but also other findings, this episodic activity in radio quiet AGN, I think may make them really efficient agents of AGN feedback. So because you have this kind of jet plus wind happening on, the timescales that we're talking about are now, decadal timescales actually. So decadal timescales to a little larger. So from 10 to the 3, 10 to the 4 years, things are happening on these in these radio quiet AGN, which will definitely influence their medium. So yeah. Episodic is important.
Okay.
Long live India and France friendship.